All right, today's lecture is on the irreducibility of the moduli space of curves. And but first, let's recap where we are. Right, the whole course is targeted on proving this theorem, and we know everything but irreducibility and projectivity. And so these are the contents. The irreducibility we'll cover today, and projectivity we'll summarize on Monday. And maybe this comes with a caveat that, at least for the properness, we only prove properness in characteristic 0. Right? We didn't. It is true more generally. It's true over Z, and we'll actually use it. So today, one of the ideas is we'll use properness actually over Z to imply irreducibility in characteristic P. But okay, so yeah, today's outline, today's goal is to cover irreducibility, and let me just summarize like the overall outline of today's lecture. So there's 4 parts, and we're going to begin on sort of just a summary and a background on branch covers, like branch covers of smooth curves C mapping to P1. And we're covering this because this is an important feature in a number of these arguments. So namely in the argument 2, 3, and in Fulton's argument here, use the concept of branch covers. And if you remember back to the very first lecture, I was sort of emphasizing kind of that branch covers are an important way to think about smooth curves. They give you a handle on its geometry, and we even summarized Riemann's argument using branch covers that the dimension of MG was 3G minus 3. And so they'll feature again today in a very important way. And so the first argument I'll give sort of a topological one, or at least there's some topological ingredients, and dating back to the 19th century. So it's due to Klopsch and Hurwitz. So this is a characteristic 0 argument that does have some non-algebraic input. And then the next argument we'll give is sort of an argument appearing in Fulton's appendix to this Harrison-Mumford's paper on immiscible covers, namely the paper on the Kodaira dimension of MG. And this has the advantage of it's characteristic 0 and completely algebraic. And right, so that the third argument will be Fulton's appendix. And then I'll try to summarize sort of some irreducibility arguments. And from 1969, there's these 2 papers, one by Delina Mumford, where they presented 2 arguments proving the irreducibility of MG, and then Fulton's paper appearing in the same year. They all, so these methods, these are valid in characteristic P, and they reduce, so they show it in characteristic P by reducing to characteristic 0. And in Fulton's case, it only works if the degree, if the prime is larger than the genus, or G+1. So for primes sufficiently large. Right, so we're going to cover these 3 arguments, but like if you note, I'm first covering the classical 19th century argument, and then I'll go. I'm going to cover first the Fulton's appendix, because I think it's sort of more. It builds on a lot of ideas introduced in Delina Mumford's paper as well as Fulton's 1969 paper. But I feel like it's the most conceptual. It's also completely algebraic in characteristic 0. So I'll present that, and then I'll just at the end summarize these arguments from 1969. But I do want to highlight that sort of that compactifications play a crucial role in these arguments. These arguments exploit the compactification.
Jarod, can because I have to leave early, I feel like I should have asked you this before, but I mean, I've seen some of these, but maybe I never looked at some. I presume the argument in the end is going to be philosophically, you take your curve and you want to show you can break it. And as long as you can break it all the way down to trivalent genus 0, and the entire space is smooth and you can connect all of those, then you win. Is that most?
Yeah, that's exactly right. So this is why why the compactification plays a role. Like maybe I'll draw a little like a picture maybe with this like cartoon picture with what the argument Robbie was trying to explain. So if this is MG, it's not compact, right? You have like smooth curves in here. And what we've done already with stable curves is compactified it. So you have this boundary consisting of singular curves. So these are our singular curves on the boundary. And the idea is sort of to show that you can degenerate to the boundary. You pick your favorite smooth curve and you show that you can sort of degenerate it to the boundary. So if someone else picks another curve, you can also degenerate that to the boundary. And then the goal is to show that the boundary is connected. And so you kind of can further to connect those points. And so that's, yeah, I think I mean, yeah, that's the crucial reason why compactifications and are useful here, because it allows us, yeah, to connect them by breaking. Right. And right, and so the one of the struggles in these arguments is showing, in fact, that this works, that you can degenerate a smooth curve to a singular stable curve, right? And this is the main feature of the third argument I'll be giving. Any other questions on like the outline or before I begin?
Yes, is MG irreducible?
Sorry, I missed the.
Is MG without the?
Oh yes, MG
is MG
irreducible? Yes, MG itself is irreducible. I'll comment on kind of the equivalences in a second. In fact, that's the first thing I want to say. It's a good question. Actually, I also wanted to preface this lecture by saying that I'm not really an expert in these irreducibility arguments. These are all very classical. Some dating back to 1872. All of these, but I have spent some time over the last week reading these papers, and I also benefited immensely from a conversation with Eric Larson. And so this is just, for what it's worth, my attempt to summarize these irreducibility arguments. Right. So, right, the goal is to show that NGN is irreducible. And so my first remark is that because the stack is smooth, and in particular normal, it's equivalent to showing that it's connected. And since NGN bar is a family of curves over that you can reduce the connectedness of MGN bar to the connectedness of MG bar because of we have these maps between them, and they all have connected fibers. And then to relate this to the connectedness or irreducibility of MG itself. So to show that MG bar is connected, it's the same as knowing that MG is connected and that it's dense in MG bar. And so all of these statements in remark 1 have been at the stack level, but we also have a coarse moduli space. And if you take that, then because these coarse moduli spaces identify the underlying topological spaces, that and these statements, the very nature of these statements are topological. All these statements are equivalent to the corresponding statements on the coarse moduli space. Right, and over here, I sort of wanted to emphasize, why do we care? I mean, to me, this is one of the most important results in the moduli theory of curves, because it tells us that because MG is connected, the genus is the only discrete invariant. So it sort of, this is obvious, but it rules out like MG looking like, having multiple components consisting of smooth curves. I mean, I think in the very beginning, like the genus was our first invariant, and in the case of curves, you sort of get lucky that it's the only invariant. And the second statement that, so that's on the connectedness of MG. The fact that MG is dense in MG bar is sort of the statement that there's no component of MG bar consisting entirely of singular curves. So it sort of rules out having maybe, or maybe this is your MG, and it rules out like maybe having having a boundary here, and then perhaps an entire component consisting of singular curves. And because we know it's smooth, it also sort of rules out the case where, that these sort of intersect, where there's like an irreducible component of MG. So we know that, yeah. So it rules out like having an entire component consisting of singular curves. And so the arguments I'm going to summarize, I'm trying to emphasize algebraic approaches, even though like the first one, which is probably the most conceptual, intuitive one, has one non-algebraic ingredient. And of course, there are many other arguments, and I'm not trying to give sort of systematic summary of like other topological or analytic arguments. Like you can also use the Teichmuller space, for instance, to get at the irreducibility. Right, but an important ingredient in a number of these arguments is using the theory of branch covers. So the first component of this lecture is going to be an introduction to branch covers. Okay, so a branch cover of P1 is the data of a smooth and connected curve together with a finite map to P1. And often we let D be the degree of F. And in characteristic P, we want to rule out inseparable field extension. So the function field is a separable finite extension of fields. And maybe the first remark is that, this map F is a tau precisely where is a tau, okay, maybe, yeah, at points P, where the sheaf of differentials vanishes, the relative sheaf of differentials vanishes. And so this relative sheaf of differentials controls where the map is not a tau, namely where it's ramified. And we say that F is ramified at a point P of index E if the length of the localization of the sheaf of differentials at P has length E minus 1. Right, an example to keep in mind, at least this is like, I'll just give the local example where you have maybe X being A1 mapping to A1 by X goes to X to the D. And if you just compute the differentials here of X over Y, you see that if I have coordinates X, it's generated by dx, but subject to the relation that d times x to the d minus 1 dx is 0. And you see, so if the characteristic doesn't divide d, then you see that the length at the origin is precisely d minus 1. So this would have ramification index d. But note that in certain characteristics, this is like the Frobenius map, and it's not tamely ramified. Right, and then this allows us, so we then use this relative sheaf of differentials to define the ramification divisor. Maybe you just take like it's set theoretic. You take the support, but with the multiplicity of the length of the ramification index. Right, and then the natural sequence on differentials, you have this short exact sequence here, and like since we're on a curve, and both C and P1 are smooth, you get this. These are just line bundles, and you have the corresponding relation as divisors. Right, and if you just take degrees of these divisors, you get Riemann-Hurwitz. So this is, again, D is going to be the degree of F. And so just computing the degree of omega C is 2G minus 2, where G is the genus of C. And therefore, this is identified with the degree of the pullback of the sheaf of differential. So you multiply the degree of omega on P1 by D. Whoops. So this is D times minus 2, and then plus the ramification divisor R. And so you get that the degree of R is 2D plus 2G minus 2. And this is the content of Riemann-Hurwitz. All right, and then moving on, we want to restrict to particularly nice branch covers. So we want it to consider simply branch covers. So yeah, in the next slide, I introduce, so we call a branch covering simply branched if every ramification index is 2, if every ramification point has index 2, and that there's at most one ramification point in every fiber. So this is a picture of something simply branched, where you look at that the ramification points here are over distinct points in P1, and they're all just doubly branched. But these examples at the bottom, these are not simply branched, right? Because here you have 2 ramification points over the same point, and here you have a ramification index of 3. Right, so if you have a simply branched covering, then Riemann-Hurwitz implies that a simply branched covering is ramified over this number, which I'm calling B, 2D plus 2D minus 2 distinct points in P1. And so this is so it seems like a nice notion, but we need to show that that smooth curves have simply branched coverings. So this is the content of the first lemma, that every curve. The content is I take a smooth projective connected curve of genus G and a line bundle of sufficiently high degree. You can make the bound explicit if you want. And then the statement is that for a general subspace, 2-dimensional subspace of the sections of L, that the induced map defined by this linear series is simply branched. And the argument, I won't go through it in full detail, but it's just a dimension count, right? Because you look at, so you know that by Riemann-Roch, you know that the dimension of global sections of L is D plus 1 minus G, and so therefore the subspace of the Grassmannian of 2 planes in this vector space has dimension 2D minus G minus 1. And so the strategy is to show that if this linear series is not simply branched, then it fails. The conditions saying that it fails to be simply branched are going to be lower dimensional, right? So what we need to show is that if the cover is not simply branched, then we know either there's a base point, or there's a ramification point of index greater than 2, or there's 2 ramification points in the same fiber. So each of these needs to be treated separately. Maybe I'll just explain quickly why B the condition of B has smaller dimension. So let's just look at case B. So in this case, there's going to be a ramification index, a point with ramification index at least 3. So there exists a section in V such that S actually vanishes to order 3 at some point. And therefore, if you want to compute the dimension of subspaces V in the Grassmannian, such that this map given by P satisfies B, we can compute this as the dimension. So we want to look at, we need one section or vanishing to order 3. So let's just view it up to scalar. So projectivize this space. And then you need one other section and maybe up to scaling if you in the quotient of a given section here. So and then if you do this dimension count using Riemann-Roch, you just compute that this is, so this dimension using Riemann-Roch. Okay, I'll cheat. I have it written here. D minus 3 plus, and this is D minus G and then minus 1. And then if you compute this, this is 2D minus 2G minus 4, which is strictly less than 2DG minus 1. Right, and then for cases A and C, you argue similarly. You just compute the dimension of that condition, and you show it's less than the Grassmannian. So this gives us the existence of simply branched covers, sort of the starting point for these arguments.
Jared, I thought in characteristic 2 there weren't simply branched covers. Do you know if this goes wrong somewhere or if I'm misremembering? Because I thought they were always wildly ramified.
Right. I don't remember. I mean, I don't remember. I need this in characteristic 0, but I'm not. I'm not sure.
Thanks.
If this breaks down a positive characteristic.
Also,
Let me just add this. Oh. Let me add a characteristic 0 assumption here. That's a fair question.
Also, just at the end of this argument, do you really want that if you like added 1 to the left-hand side, it's still less than the right-hand side because like the point could be anywhere on the curve?
Oh, right. Yeah, good point. And I guess we're lucky here. Yeah, because this is actually 2 less, yeah. Right? Because the point could be any, okay. Yeah, Hannah wants me to add a -1 here because the point adds a curve. Yeah. Thank you. Are there other questions, corrections? Okay, so on the next slide, I have other important, some other properties simply branch covers. The first is that simply branch covers, if the degree is greater than 2, have no automorphisms, meaning that there's no automorphisms of C over P1. And I'm not going to spell it out completely, but the reason is that, an automorphism over P1 would fix the branch points. The 2D plus 2G minus 2 branch points. And there's just a fact, classical fact about curves, smooth curves, is that there does not exist any non-trivial oughts fixing more than 2G plus 2 points. And so as long as D is greater than 2, there won't be any automorphisms. That's not such an important fact for this lecture, but I just wanted to state it. But it does allow us to define. So I'm going to look at now the moduli space of all simply branched covers. I define that as h d little b. So little d is the degree, little b is the number of branch points, and there's a relationship between b, the genus, and the degree. And so we can define this either as a topological space, or because there's no automorphisms, as an algebraic space. And sort of the important point here is that there's maps, that this maps both to MG and to the symmetric product of P1, where here, if I'm given a simple branch covering, I just forget the covering, I can map it to C, or I can map to the B branch points. So this is here, this is the locus. I'm taking the symmetric product because I don't want to have the points ordered. These are B unordered distinct points. And yeah, this is bijective to the projective space of dimension B moving the discriminant hypersurface. And so, yeah, so if you're just interested in this Hurwitz space as a topological space, you can use this to define the topology on HTP. Right, and what we want to do, what we want to know is that this map is finite and étale. So in characteristic 0, this is the third lemma. Here I did add the characteristic 0 hypothesis. Yeah, is that this map is finite and étale. In other words, this map is a covering space. And the reason we care about this is that, you know, the first lemma implies that the first lemma we proved implies that there exists a simply branch covering of C. But now, because this map is finite and étale, as I deform the B unordered points, I can deform the curve with it. So what this lemma will allow us to do is to show the lemma implies that there exists that, let me write it this way, that any C to P1 can be deformed so that the branch locus is general. Right, and so let me just give you a hint of these ideas. You can approach it topologically or algebraically. And I'm going to prove the étaleness. I'll skip the finiteness, which is treated, there's an argument I'm going to give later, which is essentially the finiteness argument. But so topologically, so we have in this picture here an example of a simply branched covering, and what we need to show is that if I wiggle these points around, then I can wiggle the cover as well. So let's suppose that I have a point here, Q1, and I'm just moving P1. I'm just going to do the argument for one point. I move P1 a little bit to this point Q1, and I want to show that I could deform the cover. And this is all topological, so I can sort of take an open disk around these points. I guess that, oops. And then looking at in an open neighborhood. And then I could just move this cover to another point, and then I form the global cover just by realizing, you know, like away over other opens here, this is just the trivial cover. So I just glue back this to create the purple curve. I can just glue it to the to the complement, because it's topologically trivial. Is this okay? I mean, it's much easier than the algebraic argument, because, yeah. And so algebraically, what we need to show is that, that they have, that there's a bijection between, say, first order deformations of the cover and of the points in P1. In other words, this is the induced map on tangent spaces of this cover. And since they're both smooth, to show that this map is a tau, it suffices actually to show that, that it induces a bijection on tangent spaces, or in other words, these first order deformation spaces. And on the right-hand side, right, these are just B distinct points in P1. So this is B-dimensional. And I'm just going to compute the dimension of this space. So this space, you can show deformations are classified by sections of the normal sheaf to F, where if you look at the pullback map of the tangent sheaf of C mapping to the pullback, the tangent sheaf on P1, and then NF is just the quotient. And so to get at the dimension of this vector space, I look at the corresponding long exact sequence, and H0 of TC vanishes because the genus is greater than 2, is greater than 1. So I get a map from H. So this induces a short exact sequence of vector spaces from H0 of the pullback of P1 to H0 of NF to H1 of TC. And actually, this sort of has an interesting interpretation in terms of deformation theory. Like this middle term is deformations of the cover. This maps, if I just forget the cover, we already know this classifies deformations of C. And so this is this map here is the forget-from map from the covers to the curve. And meanwhile, this is sort of the kernel. This is deformations that of sort of the map with that fix the source and the target. And so computing the dimensions of these, this we already computed with Riemann-Roch. This is 3G minus 3. Here, Riemann-Roch implies that the tangent bundle on P1 is O of 2. So that has degree 2. I pull it back by F, so it has degree 2D. So therefore, by Riemann-Roch, it's 2D plus a 1 minus G. And if you add these up, you get B. And so at least this shows that maybe you should expect that it to be bijective. There's more work involved in showing that you have to show that this map actually induces this bijection. I'm just trying to give you a hint at these arguments.
So the second map in the short exact sequence, is that just the tangent map from the Hurwitz space to MG?
Yes.
Okay, so that
Yes.
shows that that map is smooth.
Oh, yes, for instance, yeah. Right, yeah. Okay, what I can say is that, that was the eraser. What I can say is that this is the induced map on tangent spaces to MG, right? And you want to say that because it's surjective, that map is also smooth. Oh. I'm putting this on YouTube, so let me move on. We can discuss it at the end.
Are we making some assumption about D being large?
I'm assuming D is sufficiently large, yes.
Okay.
Yeah, I'm always taking D to be sufficiently large, yeah. Are there other concerns here? Okay, let me tell you that. Okay, so this completes what I wanted to say about the background of simply branch covers. Let me try to explain how this is then used to get irreducibility with the Klipsch-Hurwitz proof. Okay, so here are the references. Yeah, our Klefsch's paper, Hurwitz's paper, and then there's in Fulton's 1969 paper, which we'll get to later. He also gives sort of a modern treatment of these proofs, and ultimately, his proof is in positive characteristic relies on the characteristic zero statement. So you can read about it in that paper too. So there's the one result we need that's sort of non-algebraic is the Riemann existence theorem. And we'll need it in this following form, that there are bijections between algebraic branch covers, topological, and holomorphic. Right, and maybe it should be clear, it should be obvious that any algebraic cover gives you a topological one, same with any holomorphic. But if you're given a topological branch covering, you can use that to define a holomorphic structure on C, inducing it from the holomorphic structure on P1. So it's not hard to see that these are actually equivalent. So sort of the content of this in the hard direction is that holomorphic coverings are algebraic. Right, and we'll also need the following ingredient from topology of we'll look at the monodromy action. So let me explain quickly, even though that may be familiar to many of you. So I take a curve, and so then and I let B in P1 be the branch locus. So that's the red points down here. And let's take a point. Let's take a point P downstairs and a preimage Q. And so that and note that my picture is one-dimensional, but that P1 over C is a two-dimensional. So let me view it as a two-dimensional surface, and then what I'm going to do is take loops around. So let's take a loop starting at P going around here, gamma. So gamma is an element of the fundamental group of P1 of C minus the branch locus based at P. And since this is a covering outside B, you can lift this path gamma to C, and if you trace, you can trace Q under the lifting of this path, right? What that gives you is, if you think about this, it just goes up, and maybe it lands here, Q prime. So tracing points in the fiber under lifts of a cover gives you another point, right? This is Q prime. So in other words, what we have is a map from the fundamental group or we have an action, whoops. We have an action on the fiber, F inverse of P. All right, and this fiber consists of D elements. And the action explicitly is just gamma times Q is Q prime. Well, another way to say this is that, we have a group homomorphism because every group element just permutes the fibers. You have a map to the symmetric group on the fibers, SD. It's called as rho. This is a group homomorphism. And we also know exactly what the fundamental group is. I mean, this is a fundamental group calculation that I could do. This is just generated by loops around each of the branch points. And since it's P1, you have to add the relation that this is 1, where here sigma I is just a simple loop around the ith point in B. And then an important fact about this bijection between coverings and maps from the fundamental group to the symmetric group is that C is connected if and only if the image of rho in SD is a transitive subgroup. And keep in mind, in our definition of branch coverings and of simply branch coverings, the curve is connected. But under this correspondence works more generally. And if you think maybe about the extreme case where you have a trivial covering where so it's completely disconnected, then this fundamental group, then this map group homomorphism rho maps onto the identity. This is not hard to see this correspondence.
But are we just considering C to be smooth?
Yeah, C is smooth here.
For this last.
Yes.
Okay, because in the picture it is not. Yeah,
right. No, that's a good. Okay. No, C is smooth. Even in the picture, it's smooth. C is smooth. I mean, it doesn't. Yeah, it has sync. This map has. Yeah. We arrived at this issue before. Like, I'm drawing it like this, but there's not a singularity here. This is just. I'm drawing. This picture is drawn as an illustration of the map, not really of the curve. It's the same of like, think about the map A1 to A1 where like X goes to X squared.
Thank you.
But yeah, so far everything C is smooth in this whole story here. Right, and so so the upshot of this is that we have this nice conclusion that for any subset B, these are the branch points. So capital B is always the branch locus, little b is the number of points. And so we have a bijection between branch covers and group homomorphism such that the image is transitive. Yeah. Right, and maybe to be, so here, by the Riemann existence theorem, you could take these to be algebraic or topological. And let's see, to be precise, this equivalence is up to inner automorphism. It's not so important for today's lecture, but yeah, it's up to inner automorphism, that is conjugation by elements of SD, right? Two group homomorphisms are equivalent if you can conjugate by SD. And this morphism restricts, so we have this bijection, and if you look at the locus of simply branch covers, this maps then bijectively to ones where the condition that it's simply branched, that is that there's only ramification index 2, translates, if you think about it, to the condition that the image of these simple loops, sigma I, in SD are transpositions. All right, so I think we now have the background to cover the Clebsch-Hurwitz proof. But yeah, I'll pause for a second. Okay, so this picture here reminds us what we have. And our goal is to prove this theorem here, that the Hurwitz space is connected over the complex numbers. Right, and I think it was the first lemma, proved that this map was surjective, right? That every curve, as long as you take here D is always sufficiently large, then every curve admits a simply branch cover. So this map is surjective. And this implies that because this map is surjective, the image of something connected is also connected. So this irreducibility of the Hurwitz space gives us that the connectedness of the Hurwitz space gives us the connectedness of MG. All right, and so I'll walk you through this proof here. So I'm just sort of recapping things we've already known here. So first we know the fundamental group of the complement of the branch locus has this explicit description. And here to remind you, sigma I is a simple loop around the ith point. And we also have seen that the fundamental group acts on the fibers of a branch covering. That is, this is simply branched over B. The fundamental group of P1 minus B acts on that fiber. And similarly, we've shown that this morphism I've called beta upstairs is also a finite in a tau cover. So for the same reason, you have this monodromy action of the fundamental group of the complement. So this is the fundamental group of the complement of the discriminant locus. And it acts on the fibers of this map. So that's just for notation. Let's introduce terminology here. So I'm defining HD capital B to be the fiber under beta. So yeah, maybe here in this picture upstairs, we have B and its fiber is HD capital B. And right, so yeah, so HD little b is the union over all of its fibers. And so, yeah, so what I'm trying to get at here is to looking at a reinterpretation of what this fiber is. So by definition, it's the inverse of capital B. This corresponds to covers that are simply branched over capital B. And we've seen on that previous slide that this corresponds to group homomorphisms, such that the image is a transitive subgroup, and such that the image of each of these simple loops is a transposition. So this gives us this useful combinatorial description of this fiber. So we could think this map is determined by the image of these simple loops, their transpositions. So we have the locus of B simple transpositions. Transpositions, and their product needs to be 1. And we're after the connectedness of this Hurwitz space, and this is equivalent to the transitivity of the action of the fundamental group on this fiber. So this gives us now a combinatorial strategy to prove connectedness. And so I've tried to explain this over here. So what we want to do, we want to show that this action is transitive. So we're just going to like cook up explicit loops in this space that act in a prescribed way on B ordered transpositions. And namely, there's like a particular ordered set of transpositions here that will show that every element can be moved to. Let's call this guy tau star. So by constructing enough loops and playing around, we'll move any element in the fiber to this guy. All right, so how do we do this? So here's my picture. So I'm going to define a loop capital gamma I from 0, 1 to the unordered points, distinct points in P1, where what I'm going to do is, all I want to do is swap the I and the I plus 1 point. So I'm going to choose paths gamma I and gamma I prime, not intersecting, so that they go, in those directions. And then I define this a loop in the space of B unordered points by I fix so that the first I minus 1 don't move, and then I just exchange the ith and the I plus 1th. Okay. And then what you need to check, okay, here is, I'm not going to give all these details, but you check 2 things. One, you check that this action, if I act by gamma I on transpositions tau 1 to tau B, it has the effect of fixing the first I minus 1, and then it conjugates the I plus 1 guy by I, and then the I plus first guy. It sort of switches the I plus 1 transposition and the I transposition, but it conjugates one of them. Tau I, and then tau I, and then tau I plus 2, and so on. I think that's right. And then it boils down to the following combinatorial problem: is you need to check that you could by applying gamma i's in the right order, in some order can move. You need to show that you can move any, transposition, sequence of transpositions to this particular one, tau star. And that's sort of just a combinatorial problem. But I hope this gives you a flavor of the argument. Any questions?
And is there a generalization of this using étal fundamental group?
Yeah, I think you could probably make this. Yeah, you want to just translate this argument and using the algebraic fundamental group to get like sort of an algebraic proof on the same ideas. Yeah, I would suspect so.
Okay, thank you.
Did your transitivity of the subgroup get lost in the, you have that highlighted set at the bottom?
Oh, good. Yeah, good point. Yeah. Yeah, I think I do need to add that condition. You're right. Yeah. And yeah, and that must come up in this. Yeah, that must come up in this argument too. You need to check that. Yeah, that they generate. Yeah, that they generate transitive. Thank you, John. Yeah, let's add that condition.
More simply, why are they transpositions? Is it just?
Well, I think the idea is that because it's a simply branched cover. Like if you had a different type of branching here, like in these cases, this would be it would be like a product of two transpositions, and here it might be a 3-cycle. But you have to, yeah. I think you just have to check that directly. I don't have any other words of wisdom. Okay, so I'm now going to give, so this was characteristic 0, relying on Riemann existence theorem, but now I'm going to give a fully algebraic argument in characteristic 0. And then at the end, I'll summarize how you can get the characteristic P statements. And so this is this nice idea using the boundary that appears as an application of Harrison-Mumford's admissible covers. And so in their 1982 paper, yeah, beautiful paper where their goal in the end was to compute the entire dimension of MG, but they introduced a number of other interesting ideas along the way, namely admissible covers. So yeah, it's a completely algebraic argument in characteristic 0. And the key proposition, that the main challenge for us, is to show that every smooth curve degenerates to a singular stable curve. In other words, if you have like, there exists a family of curves, maybe a curve T and a map from T to mg bar, such that maybe T maps to C. This is maybe your given smooth curve. And what you want to construct is a curve T and a map to mg bar such that 0, or such that there's a point mapping to some C0, which is a singular stable curve. So like here, T is one-dimensional. You have a family of curves. Maybe this is your given smooth curve, and you want to show that you can degenerate it to something singular. Right, that's our goal. That's our first goal, and then we'll use the boundary in a fundamental way to get at the irreducibility of mg bar. right? And so we're going to use the theory of branch covers, namely these first two lemmas. The first lemma was just that there exists simply branch coverings for a given smooth curve C. And the third was that they can be deformed, right? So on the right-hand side, I'm sketching the proof of this key proposition. So we're given a smooth curve C. And the first lemma tells us that there is some simply branched covering of C. So we take C to start, and we cook up a simple branch covering. And then, okay, and now let's just choose an ordering of the branch points. Arbitrary choice of ordering, P1 to PB. And so this defines a B pointed curve, capital B, genus 0. Right, yeah, genus 0. And so I'm viewing B, this ordered set of points, as a point in the moduli space of B ordered genus 0 points. And basically, yeah, since I want to degenerate to a singular stable curve, lemma 3 allows me to deform this simple branch covering to arrange that the branch locus is general. So I can assume B is general, and that allows me to deform the B, this B ordered points, to a particular nice genus 0 B pointed stable curve. So B degenerates to this curve here. So this is a so in other words, i.e., there exists a family of genus 0 B pointed curves, stable curves, I'll call it D over a DVR, such that the generic fiber is B, and the special fiber is, what is this special curve? It was D0. Right, this just looks like the degeneration of B distinct points on P1 to this particular stable curve. Okay, so yeah, so maybe to summarize this picture, moving on to the next slide, we have constructed a degeneration. So this is just to remind you where we were. So this sort of explains where we are right now, this picture. We have a simply branched cover. So we had deformed our original curve so that the branch points were general. So we have a simply branched cover. C star is a smooth curve. And D star, this is what I was calling, I guess, B earlier, capital B. And I've deformed the B ordered points. So in this picture here, I have my degeneration of the B distinct points to this stable genus 0 curve. And these green lines denote the sections. And I have a simple branch covering over the generic fiber. What's missing is the central fiber here. Right, so that's the first step what you can do is you can just extend the simple branch covering by defining C to be the integral closure, like the normalization of OD inside the fraction field of the family C star. And so what that gives is a family C over D and what we'd like to understand is, so maybe there's some, that gives us some curve inside here. And we'd like to understand, yeah, that central fiber. And we'd like to understand the ramification locus of the central fiber mapping to this curve D0. like understand what's happening under this map in the central fibers. And so we'd like to understand, yeah, where is that map ramified? And so now we can use something that like some purity of the branch locus, which says that the branch locus in something smooth is always a divisor. So in other words, you cannot have sort of like isolated branch points. They're all going to be in the closure. Two things can happen. You can have you can have things in the closure. You might have branch points over nodes because those aren't smooth points. Something's happening here. Yeah, and you could also have it be branched. Let me erase this. You could also have it be branched along an entire component of the central fiber. But if it's branched over an entire component, you could do a trick similar to what we did in the proof of stable reduction, where if it's branched over a single component, then it means like that fiber is non-reduced. So you apply essentially like Abiancar's lemma, which is easy in characteristic 0, like which is you base change by t goes to t to the m, where m is the multiplicity of that component. You normalize, and then you can arrange that the central fiber is only ramified over nodes. And so what you need to check here, and this requires some details I'm not going to get into, is that the central fiber is indeed nodal. After you do this process, it's reduced and nodal, and this gives you a family of nodal curves. This is, yeah, that's kind of the outcome of this degenerating these simply branch covers. And right, so but now we have a family of nodal curves. Note that if C0 is stable, we're done. Right, because if it's a stable curve, you know, then because it maps to a union of a bunch of P1s, it cannot possibly be smooth, right? Because yeah, it would have to have multiple components, and they have to intersect at nodes. But otherwise, you can take the stable model. Because we want a degeneration to a stable singular curve. You could always degenerate to some non-stable singular curve, but yeah, we want a stable. So we take the stable model just by contracting all the rational tails and rational bridges, and we need to check that this central fiber is not smooth. And the idea is, okay, let's let T be an irreducible component of C0, not its stabilization, but the central fiber itself. It's an irreducible component. This is the one that's mapping to our D0. This is the disjoint, this is the collection of P1s downstairs. And so the image, since T is connected, it maps to some P1 inside here. And now we apply Riemann-Horowitz to this cover. Riemann-Horowitz tells us that 2 times the genus of T minus 2 equals the degree times minus 2 plus the ramification locus. And there's 2 things that can happen depending on where you're, which P1 it is, right? Like maybe in the first case, like if P1 is a tail, meaning like if it's a tail, meaning like it could be this one, then there's only one node, and there's 2 branched points, like 2 of the green lines intersecting it. And so we know that the ramification is less than or equal to 2 plus, it could be fully ramified over the node, d minus 1. In the second case, if it's a bridge, so that is, maybe it's this middle guy here, then there's only one section, but there's made 2 nodes where it can be fully ramified. But actually, in either case, like this is the greater number here. So you get that, let's see, 2 g minus 2 is less than or equal to minus 2d plus 1 plus 2d minus 1. And what this calculation, if you do this right, let's see, this is minus 1 here. Yeah, and yeah, it forces the genus of t to be 0. So so maybe I'll finish in this little box here. So this implies every component of t is a p1. And that implies that like the stabilization of it is nodal. And yeah, that's what we want. Like we said, yeah. There are other ways to make this argument work, but this was sort of a nice, particularly nice degeneration to a curve where we can where Riemann-Hurwitz sort of simply shows that that the stable limit is not smooth. Any questions on this?
Are you using that M0B bar is connected to find this degeneration?
Yes. I'm using the understanding of the boundary of M0 B bar, right? And using the fact that the analogous question of degenerating to a singular stable curve there is much easier because it's just everything's on P1. You could just let the sections collide, they blow up, and you could just explicitly exhibit it. Exactly. Yeah, P1 is much easier than an arbitrary smooth genus G curve, and that's sort of why branch covers are so powerful. Anyway, so this only completes this degeneration argument. Let me complete the picture of showing how the compactification and this result implies what we want. So we've already shown this first proposition: every smooth curve degenerates to a singular stable curve. And now we need to show that the boundary, the next part is showing that the boundary is connected. And this is sort of a proof by induction. Recall that this delta is what we were denoting this complement here, or I could define it as the complement. And this consists of singular curves, which we had defined as, we defined these guys last time. And we call that delta 0 was the image, is the irreducible singular curve of m g minus 1 2 bar to mg bar, and then delta I was the image mg bar. And then by induction, we know, by induction on the genus, we know each delta I is irreducible. But we also know they intersect. Right, for each, for instance, like if I take a genus I curve and then a component and then a G minus, maybe this is a genus I, also has a genus J. So if I take this is in the intersection of delta I and delta J. And likewise, I could take a genus I component and then something like this, and then this would be in delta intersection of delta 0 and delta I. So we see that these are non-empty. And this allows us to conclude that mg bar is connected. Right, and not maybe a sketch of why this works, I think, is that if this is So basically the picture I gave in the first slide. This is MG. We have, so this is the locus of smooth curves. On the boundary, you know, maybe here is delta, whoops, is delta 0, here, and sort of they intersect, right? Maybe this is delta 0, delta 1, and so on. And so the game you play is to show that the MG bar is connected. If you have any two curves, maybe C and a C prime, you apply the first proposition to degenerate it to the boundary. So maybe this goes to here, and then you degenerate C prime to the boundary. But now you know that all of the components, they intersect, so you can degenerate further to here, and you get that MG bar is connected. But this argument actually shows more. Let me just tell you, like, what Deline, what Harris and Mumford were interested in. The limit that we constructed, C0 mapping to D0, is what's called an admissible cover. So if you do a careful analysis to see what kind of what limits you get, what you get is something. It's what this means. So I guess you take it as a definition of an admissible cover is two things. So here D0, recall D0 is an M0B bar. So it's a union of rational curves meeting in nodes. And so this cover must be simply branched away from the nodes. And then over the nodes, it could be branched over the nodes. The branching has a prescribed form. It looks like the local calculation. It just looks like kind of a default cover of a node. I say x goes to x to the m, y goes to y to the m. But the upshot of this is it kind of gives you a nice way to complete this picture we had earlier, or compactify that picture we had earlier. Namely, we have you can define a stack of these admissible covers. And this maps by forgetting the cover to MG bar. And on the other hand, it maps onto M0B bar. And this map is finite, it's subjective. And so this kind of gives you a compactified picture of that diagram we were using earlier. And it's sort of, yeah. It's sort of nice because if you play around with D and you can define particularly nice loci in MG bar, and this was Harris and Mumford's goal was to define divisors in this way so that, and then compute, and then they actually computed the divisors in terms of other, in terms of, say, the boundary divisors, and then we're able to show that the canonical divisor was big, and that therefore, when G was sufficiently high, it's general type. Anyway, here I'm just interested in the connectedness, so yeah. Any questions on this?
So I have a question. So given two curves, if I want the base to be irreducible, can I find the family in which the base is irreducible and containing the two given curves?
Yeah.
You showed that I can find the base if I don't ask it to be irreducible, right? Because you. Yeah,
but this sort of, that's right. But I mean, you could take the universal base. You could take MG bar if you want.
Okay, but
if you take the universal family of curves over mg bar, we've shown mg bar is irreducible. So that.
Yeah, but if I want it to be a scheme, I mean, I have two curves and I want a family of curves in which the base is a scheme, irreducible, and containing both the curves.
Do that. You can do that as well, right? Let's return to that in the discussion. I only have like one. Yeah, I'm basically going a little slower than I expected, but I'm about done. I just wanted to give a summary of some other arguments.
Okay.
Right. So I wanted to sort of go back in time. You know, what I had just presented was an argument from '82. Now I want to show sort of how the story started in '69. So there's 69 was an incredible year for mathematics, and like Deline Mumford's paper and Fulton's paper. So what I want to quickly summarize is Deline Mumford's arguments. They gave two different arguments, and Fulton. And actually something, I meant to highlight earlier. I mean, this is the paper that introduced stacks for the first time. And they used algebraic stacks in some way in their paper, but it is not actually essential for either of their arguments. But it's really the properness, it's the compactification that's really relevant. And then, and so both papers, interestingly, they show that the mg bar is irreducible in positive characteristic by reducing it to characteristic 0. So both of them ultimately relied on either the irreducibility from the Teichmuller argument or this Clebsch-Hurwitz argument. And so the first argument, maybe it's the simplest here, just conceptually, is that what they showed is that mg bar is smooth and proper over spec Z. And that alone implies by the following fact that if you look at the number of connected components in a fiber, it's constant. And so you can immediately conclude that since mg bar, the fiber over C, is connected, you get connectedness of any fiber. And in fact, like if you have a map, okay, if you drop the smoothness assumption, and if you just have, say, proper and flat, then this function is lower semi-continuous. It can drop down in closed subsets, or at particular primes in this case. But to get that it's constant, you don't need smoothness. Having like geometrically normal fibers is enough. So in fact, this argument could have worked if you applied this to the coarse moduli space. Right, and their second argument, okay, so that's one argument. Second argument is not too, different. And I'm sure they had many other arguments in mind when they wrote this. There was less available at that time, but so in the second argument, they sort of used the boundary divisor as we did in our previous argument. So the idea was you first show that for any field, that there doesn't exist any proper connected components of mg. This was actually the hard part, that there's no proper connected components of mg, and this is the part that uses a lot. It uses the existence of coarse moduli spaces of mg over Z, in fact, and they relied on GIT. But you wouldn't say that their proof this was not a GIT construction as we would call it today. It appears in Mumford's book GIT, but he proves this without using really the Hilbert-Mumford criterion and sort of the standard setup that we know as GIT. It's that sort of an ad hoc method using covariance. But and interestingly, actually, at that time, this was 1969, Mumford's theory of GIT wasn't even known to work in positive characteristic. It was only later in like the late 70s that Habush resolved Mumford's conjecture, which allowed it to go through. And then the relative GIT setup wasn't even shown, wasn't shown a couple of years later until Seshadri. So this is not, so it's using a result in the book. And the point was, the MG, and it uses a compactification. So Mumford also showed that MG was quasi-projective. So you can just take a projective compactification here. The projectivity is not important though. You could also have, they could have also applied Nagata compactification to get something proper, which was a result that had been proven also that decade. Anyway, but now, then they use the characteristic zero result. Now X is projective over Z. And so now you use sort of a similar connectedness result to their first argument, where you show that using the characteristic zero statement, that X being connected over the complex numbers implies that X over any finite field is also connected. And then finally, it relied on actually showing that MG itself was not proper. But by using not degenerations of curves, but using the degenerations of their Jacobians. And then then the next step was to show that there doesn't exist a connected component consisting entirely of smooth curves. So this follows more or less from step 1 in stable reduction. And then finally, these two steps, 1 and 2, essentially, what they do imply, what our key proposition, namely that smooth curves degenerate to stable curves. And then they conclude in a very similar way that using the boundary, that they conclude that they argue that the boundary is connected, sort of similar to, but in a little more ad hoc way, because in that paper they didn't introduce the end-pointed versions of these moduli spaces. They didn't have the gluing maps between them, but the argument is essentially what is the same. And finally, just to go very quickly over Fulton's argument in 1969, just to give some historical perspective, his approach was not using, he didn't use the properness, but his strategy was he wanted to define the Hurwitz scheme. He defines it over Z. And so he showed that our picture that we had over the complex numbers extends to a picture over the integers. And he showed that this map was finite as long as the characteristic was bigger than the genus. It actually fails. Yeah, there's a discussion in that paper. It's just not, it's not finite and low characteristic. Right, this is the map that takes, a branch cover to C and this to the branch points. And then rather than relying on the properness, he sort of showed that a reduction theorem where he showed that since this map is finite in a tau, the connectedness the connectedness generically of this Hurwitz space implies it over a finite field. And there's quite a bit that goes into it, but that's sort of my attempt to summarize it. So I'm going to stop the recording now, and then we can have a discussion.